Hello, everybody. So today I'm just going to be doing a quick, not can't really say quick, but just a lesson on approximation and computation of area. So, what is approximation? Well, approximation is one of the first techniques taught in integral calculus because it is one of the first ways we learned how to how to estimate what the area under a curve is. And the way that it's done is you split the area under the curve into multiple different rectangles, and then you find the area for each of these rectangles individually, and then you add up the area of all the rectangles. And this gives you an estimate of the area. It won't be the exact area, but you will have somewhat of an idea what the area could be. So let's get right into what subintervals and what our delta x is. So let's say I split this graph right here into multiple different rectangles. Let's say I want to split it into four different rectangles. So one, two, three, and four. So don't mind my terrible drawing skills, but each of these rectangles are a different subinterval. So the overall interval is from 3 to 8, okay? That is the overall interval. So the total interval is 3 to 8, okay? But that is specifically only for this question. Now, subintervals would be from one of these points, from one of these points to one of these points. So basically, an example of a subinterval is assuming that the distance between each and every single one of these lines that make the rectangle is 1 unit, then one subinterval would be from 3 to 4. That is just an assumption, but that is just pretty much an example and how I'm going to start explaining this. So each subinterval simply refers to the start and end point of each of the rectangles. So once again, just to quickly go over what we covered, the 3 to 8 is the total interval. And each of the different intervals within this total interval that make up all the rectangles are subintervals. So, just for demonstration's sake, I am just going to say that let's just give each of these points numbers, just so this makes it a little easier for everybody to understand. This is 4, 5, and 6. Okay? So the total subinterval is from this point all the way till this point. That is the total the total interval. Now, subintervals, there are many of these there's going to be many of these subintervals. For example, there's going to be 3 to 4, that's one subinterval. There's 4 to 5, which is another one. 5 to 6, which is another one, and then 6 to 7. So overall, there's only going to be one total interval, but there can be however many subintervals. The way I like to the way I like to memorize this is that the number of rectangles there are, that's how many subintervals, because each rectangle has to have a start and end point. So because there are four rectangles here, there are going to be four subintervals. And the subintervals, like I said, are going to be 3 to 4, 4 to 5, 5 and 6, and then finally 6 to 7. Those are going to be our four subintervals. Now that we have what a subinterval is, let's figure out what this delta x here means. So delta x is one of the it's a notation that we use specifically when we're talking about approximation. And all that it represents is the distance of each subinterval. So pretty much the width of each of these rectangles. And one of the rules of approximation is that when it comes to subintervals, we always assume that each subinterval has they have the same width. And the reason that we do this is that it just simply makes our calculations a lot easier. So, how do we calculate this? Well, so width to delta x has a specific formula that we use, and that is going to be b minus a over n. So these variables might seem a little confusing, but they're actually very, very simple. So b is going to be equal to the end point of the total interval. So where does this total interval end? Well, this total interval goes from 3 to 7, and since b is the number that's being subtracted from, we always want the higher number. So you would always choose the number that it goes to, or the number farther along on the x-axis. So b in this case, just for this one, just for this graph, b is going to be equal to 7. Now a is going to be start point of our interval. That in this case, for this total interval of 3 to 7, the start point is going to be 3. So a is going to equal 3. And then finally, what is our n? Well, our n is the number of subintervals, or basically the number of rectangles there are. So for this demonstration, we have exactly 4 rectangles, and therefore 4 subintervals. So n is going to equal 4. And then the way that we can calculate the width of each of these rectangles, or otherwise known as our delta x, is by just plugging it into this formula here. So delta x is equal to b minus a over n. So b, so 7 minus a, so 3, divided by n, which is 4. So 7 minus 3 is 4, so you end up with 4 over 4. So you finally find out that our delta x, or the width of each of these rectangles, is going to be 1 unit. And that is basically subintervals and delta x. So now we're going to move on to our next part. And that is going to be the different types of approximations. So as you know, in order to find the area of a rectangle, you need two things: the width and its length, or otherwise its height. So using delta x formula, we can find our width. But how do we find our height? Well, our height, there are 3 different ways we can find this height, or to say, not technically different ways, but 3 different types of heights that we can use. So in this one here, I didn't really make any rectangles. I simply just separated them into subintervals. But on a real approximation question, you're going to get what you, if there's a graph in your approximation question, they're going to look like one of these 3 that I'm going to draw. The first one that I'm going to draw is our LN, so our left point approximation. So basically, what this just means is that um, since that the part of our rectangle that is touching the graph is simply going to be its left end. The left end of the rectangles are going to touch the graph, while the rest of them don't. Actually, that's not even correct as well. So technically, the other parts may also touch the graph, but the only point that we care about is the left point, the very most left point of each rectangle. So this is what a left endpoint graph looks like. Now, I haven't explained what endpoints are yet, but I will explain in just a little bit. So as you can see, each of the rectangles, the part that is touching the graph is the left side, or the leftmost point is the part that touches the graph. And basically, the assumption that we make is that the height of each of these rectangles is equal to the y value of that point right there. As you guys know, on every single point on a Cartesian plane has an x and a y coordinate. And whenever we're trying to find the height of a rectangle, what we do is we find out the y value for this specific point here. Each of these points, we find the y value, and that is what we assume is the height of that rectangle. Now, we don't always have to use the left side. We can also do something called a right endpoint approximation, so Rn. What is Rn? Well, instead of measuring based off of the left side, we now measure based off of the right. The height of the y coordinate of this right endpoint here, the topmost right part of each rectangle. Now, as you guys can see, the point that is specifically touching or on the graph itself is the right point of each of these. And just like a left endpoint approximation, what you would do for these is you would find out the y coordinate. What is the y coordinate for each of these points? And that is what your height or your length, whichever one you prefer to use or call it, is. Now, there is finally one other type of approximation as well, and that is called a midpoint approximation. And the midpoint approximation is very interesting because instead of having per se one instead of either having the left or the right of your rectangle touch the graph or be directly on the graph, some point in the middle is now directly on the graph. And what we do is, in order to calculate the height of each of these rectangles, you find the y coordinate of this point right in the middle. Bear with my drawing, it is not the greatest, but yeah. So instead of having either the left or the right of each of these rectangles and taking the y coordinate of that, we instead take the x and we take the y coordinate for a point directly in the middle of the rectangles. Now, something I do like to point out whenever I draw these graphs is that depending on which one you choose to go with and find the height of each respective rectangle, your answer will change. So for this graph right here, as you can see, there's actually a little bit right below the graph. There's a little bit of area beneath the graph that each of the rectangles don't account for. This means that in this specific case, our left end approximation is actually going to be less than the total area. Why? Because there's these pieces of area that we don't account for. And that is why this left end estimate is going to be slightly lower than our area, their actual area. But for the right endpoint, we also have some area. But this area is above the graph. And this area that is covered by rectangles. So what does this mean? This basically means that our right end approximation is actually going to be greater than the area beneath this curve. And this is because each of these rectangles actually covers some area above the curve that's outside of this area here. And then the most interesting one is our midpoint approximation. Why is this interesting? Well, for a properly drawn midpoint, you would actually have a little bit of area above and below. So what does this mean? Well, this simply means that your midpoint approximation could be greater or less than the actual area beneath this curve. Depending on the graph, it will change, but this midpoint approximation is actually going to be the one that is closest to the actual area beneath the curve. These left point and right endpoint, they can only be technically used as ideas of relatively what the area could be. So if I were to calculate this left endpoint and somebody asks me what the exact area beneath this curve is, the only thing I could really say for this graph specifically is that the exact area of this curve is greater than whatever value I calculated for ln. And the same concepts apply for Rn as well. Mn is the only one where you can say it is approximately this value. Now, I went on talking about what all of these are and what the height of each of these rectangles is, but I didn't talk about how to find the height of each of these rectangles. Well, what we do is we first find something called endpoints. So you guys remember how each of these subintervals have a start and end point? Well, that start and end point is how we find the height of each of these rectangles. So as you know, approximation is used to find the area between a curve and the x-axis. So what does this mean? Well, this means that this line right here has an equation. So just purely as a reference, we're just going to say that just this curve, let's just say it's going to equal y equals 2x or something. Or you know what? We'll make it even nicer. We'll just say x squared. How does this help us find the height? Well, remember, the height is the y coordinate of a point that is on top of the curve. And each and every single one of these rectangles will have a point that is on the curve. And basically all we do is we find whatever endpoint, so whatever value is down here, whatever x value. So the first thing we do is we find the x value of each of these points, and then we plug it into this function. So in this case, to find this point what I would do is I would find the x value, which I know is 3 in this case, and then I would put 3 into this equation, and then when I did that, I would find out that the y coordinate is 3 squared, or otherwise known as 9. And then from there, I would take 9 as my height. But if but let's say in a question we're only given the start point and the end point of the total interval. So this total interval. How do you find all of the intervals, endpoints, and start points and endpoints? Well, if it's a nice one like this, you could try first just trying to label, and you just assume that, let's say there's a difference of 1 in between all of them. Now, it would work for this question because I already counted it out, but let's say that instead of this being 9, this is now 8. How would I find the endpoints and start points now? Well, there is a specific formula that we use. And this is where we find it useful to have the width of each of these rectangles exactly the same. That formula to find the x coordinate of one of these endpoints is x of j is equal to a, so the start point of the total interval, plus n, so which number of triangle we're trying to find. Or actually, what I've seen some people do is just say j, and j once again simply responds to which rectangle's endpoint we're trying to find, times delta x, or otherwise known as our width. Why does this work? Well, we know that, let's say I want to find all the left endpoints. So left endpoints of this graph. Well, I already know that the very first left endpoint is at x equals 3, because that's where we start at. But let's say I want to find the second one. How would I find this x value so that I could find this y value? Well, I would first need to remember which endpoint this is. So, and the very start point is always considered x of 0. Why? Because you don't have to change, because if I plug in x of 0 here, I get 3 plus 0 delta x, meaning that my x stays at 3. I cannot count this as x of 1, because let's say I do x of 1, well, I end up with 3 plus delta x. That is no longer this point right here. It's no longer that point. Now I've moved over 1 delta x, and I'm finding this point, the x value that's right here. But we don't want that for the very first point. So always remember, the start point of the total interval is always x of 0. So I'll even write this down. Start point of total interval is x of 0. Always remember that. The x value of the start point is always referred to as x of 0. Okay? Now, I don't know, because this is not nice anymore, how would I find this point? And remember, since this is x of 0, this point is going to count as x of 1 now. So, I've already written down this from the previous explanation. as to the formula for x of 1. So just to alter it slightly to make it slightly nicer to see, that is our formula for x of 1. And as you can see, delta x is what we need. So the delta x for this is, if you guys remember the equation, b minus a over n. So we know that our endpoint of the total interval is always b, the start point is always a, and n is the number of subintervals or rectangles. So let's count out how many subintervals there are. 1, 2, 3, 4, 5, 6. So we know that n is equal to 6. So I can just write this out now. So we know that this is 8 minus 3 over 6. So you end up with a delta x of 5 over 6. I want you guys to keep in mind, you will often come in contact with fractions when you do this. So when you're doing approximation, I hope you guys get very, very familiar with fractions because you're going to be using them a lot. Most of the time, you won't be getting a delta x that is a nice number. So now that we do this, now that we know what our delta x is for this, we can find x of 1. So 3 plus 5 over 6 times 1, so just 5 over 6. And then this turns into 18 over 6 plus 5 over 6, otherwise 23 over 6. So we now know that this x value right here is 23 over 6. Now, how would we find the y value? Well, we simply just got to plug in the x value that we found into the function itself. So we're just going to go and say 23 over 6 squared. Let's see. I know my bottom is going to be 36, and then 23 times 23 is 529. Now does look more intimidating than it actually is, but if you do 529 divided by 36, you simply get 14, which is very reasonable, considering that our first y value was 9. And basically, this is how you would find the x value for each and every one of these endpoints, and then you would just plug them into the function to get your heights for each and every single one of these subintervals slash rectangles. Now, I am just going to do a practice question because I personally find that I learn better from doing practice questions than actually just listening to somebody explain it to me. So, what are the right and left endpoints if 2 and 5 if the interval of 2 to 5 is divided into 6 subintervals? Well, first thing that we're going to do always is we're just going to calculate our width because we have all the information that we need. We have interval and we have our n right there. So, delta x is equal to b minus a over n. So basically, we know that our endpoint of our total interval is our b. So we know that b is equal to 5, and we know that our a is equal to our start point of the total interval. So we know that this is going to be equal to 2. And then we know that our n is equal to 6 because it's split into 6 subintervals. So basically, all we do is we just sub in our values. So 5 minus 2 over 6. 5 minus 2 is 3 over 6, which is equal to 1 half. So delta x in this case is equal to 1 half. Now, something that I forgot to mention earlier is that right and left endpoints often are calculated slightly differently, and I'll show you why in just a second. So, this question asks for right and left. But going back to here, we can see that our left endpoint, the very first one is at A. But but let's say that instead of calculating the point on the left, I wanted to find the point on the right. Well, when that happens, our very first right endpoint is actually here, meaning that that endpoint is the very first one for our right end approximation. So, what does this mean? Well, this just means that for left endpoint approximations, you always start at x of 0. But for right endpoint, you always start at x of 1. Simply because the left is always going to be the left endpoints are always going to be the very first left endpoint will always be on top of A, while the right one has to be across the rectangle. So it'll always be at x of 1, while the left endpoint it'll always start at x of 0. So I am going to calculate our left endpoints first because because I will show you guys a trick in 1 second. So let's just write down our formula really quickly. X of j is equal to a plus j delta x. And now we're just going to sub in some values. We know our a is 2, and we know our delta x is 1 over 2. So let's start with our left endpoint. We already know that for x of 0, so our very first left endpoint, it's always going to be equal to a. So basically, our very first endpoint, our left endpoint, is going to just be at x equals 2. Now, the next endpoint, our second left endpoint, is going to be at 2 plus 1 over 2, otherwise known as, I believe it is 5 over 2. So x is equal to 5 over 2, or 2.5. That is where our second endpoint is going to be, our second left endpoint. Now, what about our second one, our third left endpoint? Well, it's going to be at 2 plus 2 times 1 over 2, which just cancels out. Which just cancels out and turns into 1. So this turns into 2 plus 1. So this is going to be at 3. X equals 3. Now, what about our third, or our fourth left endpoint? Well, 2 plus 3 times 1 over 2. So that's going to just be 7 over 2, or otherwise 3.5. Now, you guys can see a pattern already, right? The first one was at 2. The second one was at 2.5, meaning we added 0.5. Then it went to 3, so another 0.05. And then finally another 0.05 from 3 to 3.5. And basically, what I just want to show you guys is when it's a easy to compute number, when your delta x is an easy number such as 1/2, all you have to do actually is add, you just have to add delta x multiple times to get to the endpoint you're wanting. So if I want to get to, let's say, x of 5 now and just skip over x of 4, and I don't want to calculate x of 4, all I need to know is that x of 5 is 2 points away from x of 3, and it is 5 points away from x of 0. So all I have to do is, if I have x of 3 and I want to get to x of 5, I know there's 2 away. So all I have to do is I have to add 0.5 twice to my x of 3 value. So 3.5, and I would get x of 5. So just using that method, I'm going to say that it is going to be equal to 4.5. And I'm going to verify this using our formula as well. 2 plus 5 over 2, which ends up being 4 over 2 plus 5 over 2, so 9 over 2. 9 divided by 2 is equal to 4.5. So always just stick to this formula, and you can always do it very easily. And if it's a familiar number like this, then between endpoints, you simply just have to add delta x once, and you'll get from endpoint to endpoint. Now, I am just going to do x of 4 as well. Since I'm just going to directly subtract, and then I know x of 6 is just going to be 5 because I just add 0.5. Now, I do want you guys to calculate the right endpoints by yourself. So pause the video right here, do calculations, and then after that, I will get into it and do it myself. So, assuming that you have paused the video and calculated, let's get right into it. So, remember, the right and left endpoints start at separate parts. But due to this, you know that the endpoints also overlap. Because while the very first endpoint for left end is x of 0, the very first one for right end is x of 1. But x of 1 is actually also an endpoint for left end. It's the second left end endpoint, while it's the first one for right endpoint. This basically means that if you have the same graph for both questions and you're asked to find the endpoints, well, all you have to do is, if you've already calculated one, you can simply relate it to the other one. So what I know is that because it's on the same graph, I know that x of 1 for my right endpoint is going to be equal to the x of 1 for the left endpoint. The only difference is that the starting endpoints for both of these approximations are different, but the actual endpoints themselves will be very similar. So x of 1, I can simply copy it from there. I know it's going to be 2.5. And then because the interval, the delta x is the same, I can go from there and just keep on adding 0.5. Perfect. Now, something I would like you guys to keep in mind is just as the starting points are different, the ending points are also different. So, I'll do this in blue and red. So, we're going to say that red is going to be our right endpoint, and that blue is going to be our left endpoint. So the very first left endpoint is right there. And the very first right endpoint is right there. Now, the very last left endpoint is here. But the very last right endpoint is at right there. So basically, when dealing with left and right endpoint and transitioning between the two, just know that you have to take you simply have to think of left endpoint as just being shifted over by one, meaning that it starts at one place earlier and ends at one place earlier than your right endpoint. The actual values of each of the endpoints are going to be exactly the same. So x of 1 for left and x of 1 for right are going to be the same. It's just that x of 1 is going to be the first endpoint for right end approximations, while it's only the second one for left end. I'll draw a graph here as well, just to make it a little easier. Oh my. So let's say I have something like that. Once again, I'm going to have right endpoints in red and left in blue. So assuming this is A and this is B, our very first left endpoint, so x of 0, very first endpoint, is going to be there. This one's going to be x of 1. This is going to be x of 2. And then this is going to be our final endpoint because we're only going off of left ends. Now, this is where right endpoints are going to they're going to be very similar. So right endpoints, they will overlap with the left endpoints. It's just that the starting and ending are different. So as you can see, for our left endpoints, our very first one is at A, and our very last one is at B minus 1, or otherwise known as N minus 1. And why is this called N minus 1? Well, because as you can see, normally endpoints are numbered based off of which rectangle they correspond to. So 1, 2, 3, 4, and right endpoint follows that very well. As you can see, x of 1 is for 1, x of 2 is for 2, x of 3 is for 3, and x of 4 is for 4. But for left endpoints, it's a little different. Because x of 0 is actually for 1, and x of 1 is for 2, x of 2 is for 3, x of 3 is for 4. So basically what you can just see is that you take the rectangle number that it corresponds, the rectangle number that the endpoint corresponds to, and in order to get the actual number of the endpoint, which endpoint it is, you simply take the number of that rectangle and subtract it by 1. Now, that is just calculating endpoints. Now we're going to get into actually finding the height. And finding the height, again, very simple. I'm just going to go so once again, we're just going to assume that this function is x squared. And we're just going to find our n value here really quickly. 1, 2, 3, 4, 5, 6, and 7. So we'll say, for now, we'll just say that this is going to be 1 and this is going to be 8. And assuming that we've already calculated all of our endpoints, we're just going to say this is 2, 3, 4, 5, 6, and 7. So now we have the x values of all of our endpoints. And for this specific graph, it's going to be a left endpoint approximation. So we already have all of our left endpoints. We have the x values for the left endpoints. And now what we have to do is we have to find the y value so that we can get the height at this point right here, at each of these points. So this is the height. This is the height. This, 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 and this. Those are our heights. And what we're going to do to find this height is we're just going to plug it in to the actual equation of this line at the top. We're going to plug it into that equation. So if the x value for our very first endpoint is at 1, we're simply going to say our first height, or y1, is going to be equal to our function. So our function in this case is x squared. So y1 is going to be equal to if 1 was subbed in for x. So 1 squared, so 1. So this point right here is at 1, 1. Next, we want our second y value. So that is for this point right here. We know that it's already at x equals 2. So now I'm going to sub that into our function. So 2 squared. So 4. So we know that the coordinates for this and the height of this one is going to be 4. And then if you do this repeatedly, all the way until the seventh x value, sorry, the seventh rectangle, what you'll find very quickly, what you'll find very, very quickly is that it's going to look something like 3, so 3 squared, so 9. So this is going to be 4, 5, 6, 7. So 4 squared, 5 squared, 6 squared, 7 squared. So 16, 25, 36, and 49. So what you find very quickly is that it's not hard at all to find the height or the y value of each of these points as soon as you can find the x value of the endpoint. So once again, finding height, very simple thing. You take the x value of the endpoint that you found in the previous step by using this equation right here, and then you simply plug it into the function that you're given, the function of this line on top, and then all you do is you simply plug in each of the x values, and then it'll spit out a y value, and that y value is your height. Now, unlike the width, it is it is known that each of these rectangles are most likely going to have a different height. So that is basically to say, unless it is exactly a straight line, or there's any straight lines whatsoever in the function, no rectangles right next to each other will have the same height. Once again, that is unless there is any parts of the function on top that are exactly straight. Now we're going to put all of it together to get an approximation equation. And that equation is a of n. Now, mind you, this a is it's always going to be either replaced with r, l, or m, just depending on which approximation you're doing. But a of n is equal to delta x, so your width, times all of your heights added together, which is denoted by this very interesting symbol called sigma. And this is what the formula will look like. So where does this wacky formula come from? Well, let's say I have a graph of something like that. And let's say I split this into 3 rectangles, okay? Well, since so the delta x's are all going to be the same, right? We're just going to all assume that the width of each of these rectangles is the same, while let's say that the heights, let's say that for this one, it's 1, for this is 2, and for this it's 3. Okay? So y1 is equal to 1, y2 is equal to 2, and y3 is equal to 3. Okay? And remember, how do we do an approximation? We take the area of each rectangle and then we just add them together. So, what would that look like? Well, basically what this would look like is the area is equal to um rectangle, let's just say R1 plus R2 plus R3, because we have 3 rectangles and it's going to be equal to the area of each of them. I'm just going to replace that really quickly with A1, A2, and A3. Well, what is the area formula for a rectangle? Well, it is simply length times width. So in this case, it's going to look something like delta x times y1 plus delta x times y2 plus delta x times y3. Okay? That's what that would look like if we were to just individually calculate the area of each rectangle and add it together. Now, something I want to point out to everybody is, since delta x is in every single term and it's the same value, what we can do is we can take delta x out. We can factor it out. This is just basic factoring. So we end up with y1. So what you end up with is 1 times y1 plus 1 times y2 plus 1 times y3. And then if you just get rid of all the ones because they don't really change anything, you end up with y1 plus y2 plus y3. Now, this is where our summation formula comes in, or otherwise our sigma or this weird looking E thing comes in. This weird looking E, so this, what I'm writing right now, so let's say this is equal to, this is very much equal to y1 plus y2 plus y3. All this is saying is, if you sub in the value if you sub in a number for the value of j in y of j right here, for and you sub in all the values from j equals 1 to j equals 3, and you add all of them together. That's all this basically means. This just says, it's starting from j equals 1, replace the number j in this function here, and add up all of the different functions together. And that is where we get our formula. A of n is equal to delta x times summation of this. Now, I do want to note a few things down right away. And the first thing is that this x of j term here, that simply is that j value ends up getting replaced with however many, it gets replaced with the numbers in between this value here and this value here. So for example, let's say I have j equals 2 and n is equal to 3. What would this mean? Well, it simply just means that this overall thing just turns into f of x2 plus f of x3. That is all this means. It's a very simple thing. And if you guys still do have questions on how the summation formula works, I will link a video down below that properly goes through summations and explains how to do them. I just don't have the time because this video is focused on approximation. But the next thing that I did want to go over is the differences in this formula between Rn, Ln, and Mn. Because as you know, there were already some differences when calculating endpoints. And once again, there's going to be some differences when we calculate the actual approximation for each of them as well. So I prefer to usually just memorize these formulas, but if you don't want to and you truly want to understand them, I will explain that as well. So starting with Rn, the only thing that most of the stuff stays the same from the original equation. The only thing that really changes is that, so we have delta x out in front, and our summation, it starts at j equals 1 and goes to n. That is the only difference. Now, where does this j equals 1 and n come from? Well, remember how our very first right endpoint was x of 1, and we go all the way to the very last one, which in this case was x of, I believe it was 6. Well, this was x of 6, right? And there was 6 rectangles. So basically what this just means is that we go from this very first endpoint, this very first right endpoint, to the very last endpoint. That is all that this j to n means. And from and all this, yeah, and that is basically all that means. Now, ln is going to be slightly different. So the delta x is the same, because remember, this originally comes from this. The reason this delta x is out here can be contributed to this. Because it's the same value, we can pull it out of every single one of the term of every single one of the area terms for the rectangles. So once we pull that out, once we factor it out, you're only left with all of the lengths being added together. And basically, because this summation represents all the lengths being added together, we multiply this value by delta x, and that is why it's outside. So the same thing is done for ln, but the lengths that are added up start from j equals 0. So our start point, and they go all the way until n minus 1. So 1 point away from the end point of the total interval. So it's going to be 1 point away from B. But other than that, everything else stays the same. Now, midpoint is where things get interesting. Midpoints have a very unique formula for them. Now, this is actually the summation part, surprisingly, is the same as ln. But where it gets complicated is when you think about what goes within this function term. You end up getting x of j plus x of j plus 1 over 2. Why is this? Well, if our red is Rn and our blue is Ln, let's say our green is Mn. So these are the right endpoints, these are the left ones, and the midpoints, the three of them, would be in the middle, like that. And the only way to calculate that is you take the start term. So you take the first term, you take this first term, add it to that second term, and divide it by 2 in order to get this point exactly in the middle. That is the only thing that changes, and it's something that's very simple. So, if you guys want to just take a picture of these three formulas or just memorize them, whatever you guys like to do is fine. And once again, I do love solving problems, practice questions, because that's how I learn things the best. I don't really like looking at a bunch of text because it just seems very boring to me. So I am going to do a practice question for you guys. So calculate R6, L6, and M6 for the function f of x is equal to x to the negative 1 on the interval 2 to 4. Beautiful question. So we're just going to write down our important information. Our function is f of x equal to 1 over x of 1. So 1 over x and x to the negative 1 are the same thing. Then our interval is from 2 to 4, meaning that our 2 is our a and our 4 is our b. And it wants us to find R6, L6, and M6. Basically meaning that they want us to calculate it if there were 6 rectangles, so n is equal to 6. Now, what's our next step? Well, I usually like doing R6 first, mainly because it makes our life easier, and when we go for a left point, we already have all our points when we go into left endpoint. So I'm actually going to do R of 6 in red just to make it much easier to just differentiate what I'm doing. So R of 6. Beautiful. So first thing we're going to do, and something we always have to do, is we calculate delta x. So it's equal to b minus a over n. So we know our b is equal to 4, a is equal to 2, and we know that our n is equal to 6. So you end up with 2 over 6, or otherwise known as 1 over 3. That is our delta x. This is the width of each of the rectangles, or the distance between each of the endpoints. Now, once we have that, we're going to find the x value for each of the endpoints. And remember, this is right end. So the very first one is actually x of 1. So we're just going to make the general equation right for now. It is a plus j delta x. So we can substitute some values into here. So we know a is 2, and we know that delta x is 1 over 3. So what we're going to do from here is we're going to calculate the x-coordinate for each of our endpoints. And since there is 6 rectangles, we're going to calculate 6 endpoints. So this is the x-coordinates for 6 endpoints. So we're going to go from x of 1 to x of 6. So x of 1, 2 plus 1 times 1 over 3. So that just turns into 6 over 3 plus 1 over 3. So 7 over 3. That is our first x-coordinate. Second x-coordinate. 2 plus 2 times 2 over 3. Sorry, 2 times 1 over 3, which turns into 6 over 3 plus 2 over 3. So 8 over 3. Next, x of 3. 2 plus 3 times 1 over 3. So basically, this is just going to turn into 2 plus 1. So this is just going to be equal to 3 or 9 over 3, just depending on whichever one you like to use. I personally would use 3 because it's much easier when we plug it into the actual formula. But if you're somebody who likes working with fractions that much, I'm not going to stop you. Now, x of 4, 2 plus 4 times 1 over 3 is equal to 6 over 3 plus 4 over 3, so 10 over 3. Now, x of 5, 2 plus 5 times 1 over 3, which is going to equal 6 over 3 plus 5 over 3, which is going to be 11 over 3. And x of 6 is going to equal 2 plus 6 times 1 over 3, which is just going to turn out 2 plus 2, so 4, or otherwise known as 12 over 3. Now, the way to check if we got our endpoints correct is simply by comparing them using delta x. So delta x is the distance between each of the x values of the endpoints, and it's the width of all of our rectangles. So, quick way to check is the difference between these 1 over 3? And from what I can see, they definitely are. So that means we have calculated all of our endpoints correctly. So these are all of our endpoints. I am just going to outline them in a box. Beautiful. Those are our endpoints. Now we're going to do something very, very simple. We are simply going to write down our summation formula. So r of n, so in this case, r of 6 is going to equal delta x times the summation from, because it's the right endpoint, we're going to go from j equals 1 to n, so in this case, 6 of f of x of j, which simplifies into 1 over 3 times the summation from 1 to 6 of 1 over x. Now, this turns into 1 over x of 1. What is x of 1? Our x of 1 is 7 over 3. Plus 1 over x of 2, which is 8 over 3. Plus 1 over, what's x of 3? Just 3. Plus 1 over x of 4, which is 10 over 3. Plus 1 over x of 5, so 11 over 3. Plus 1 over x of 6, which is just 4. Now, if we just make this look all nice, you end up with 3 over 7 plus 3 over 8 plus 1 over 3 plus 3 over 10 plus 3 over 11 plus 1 over 4. Now, this does look extremely messy. I will give you that. It is going to be a very complicated one to solve, but that doesn't necessarily mean that it is a very bad one. So all we have to do is find the lowest common denominator. And for that, let's see. It is going to be let's see, 1 over 7. Just give me 1 second, guys. Okay, so this is actually a very annoying one. But the lowest common denominator for this is 9,240, which is a very interesting number. So I'm simply just going to go to decimal form now, because that just makes this a lot simpler. So this turns into 0.4 plus 0.375 plus 0.667 plus 0.3 plus 0.273 plus 0.25. So once you add all of that up, you simply get 0.275 plus 0.6 plus 273 plus 0.2. You're simply going to end up with 2.285, or approximately that amount. And all you have to do is multiply that by delta x now, and you end up with approximately 1.52 as our right end approximation. Actually, sorry, that is actually slightly wrong. So I'm just going to go directly here, and the value that you end up getting should be around or approximately 0.653. Now, mind you, if you aren't allowed to use a calculator on any of your tests, you will end up with very nice numbers that you won't have to do this for. I didn't really plan ahead for this one, so I ended up in this situation, but that is the approximate value that you get for the right end approximation. Now, for our left end approximation, we have already calculated delta x. We already know that our delta x is going to be 1 over 3. What else do we know? Well, we know that we already know that our left end also needs 6 x values for its endpoints, but we know that it'll actually go from x of 0 to x of 5. Because remember, in our graph that we took a look at previously, this is our first endpoint, while our last one is right here. So, we actually already have all of our values, because the x value for the very first one, x of 0, is just a. So, we have x of 0 equaling 2. And then, all we have to do is, we just have to take these identical values from our right end approximation, because they're the exact same. So, we know x of 1 is going to be 1 over 3. Sorry, no, it's actually going to be 7 over 3. We know that x of 2 is going to be 8 over 3. X of 3 is going to be 3. X of 4 is 9 over... Was it? No, it was not. It's actually going to be 10 over 3. X of 5 is 11 over 3. And now we have our 6 points. And now this is going to be very similar to what we did for our right end approximation. Simply just going to write out our formula. Our formula is equal to delta x times the summation of j equals, so starting from j equals 0, because our very first x coordinate is x of 0, all the way to n minus 1, so simply just 5, of our function, which is 1 over x of j. So down here earlier, I did leave it in this form. You don't technically have to. I mean, you could directly just write this out. It does save space, but it doesn't really matter. So we know that our delta x is 1 over 3. Now we have our fun part. So 1 of x of 0, that's going to be 1 over 2. Now 1 over x of 1, so 1 over 7 over 3, plus 1 over x of 2, so 1 over 8 over 3, and then finally 1 over x of 3, so 1 over 3 plus 1 over x of 4, so 1 over 10 over 3, and then finally 1 over x of 5, which is 1 over 11 over 3. And then when you simplify to make it all look very nice, you end up with 1 over 2 plus 3 over 7 plus 3 over 8 plus 1 over 3 plus 3 over 10 plus 3 over 11. And once again, I would use a calculator for this, but once you end up plugging everything in, the final answer that you end up getting is that it's approximately around 0.737. And now we get to have the amazing midpoint approximation. This is the one where majority of people get stuck. This is the one where they also make the most mistakes. So I am actually going to take a little bit of time doing this. So the good thing about this is that since we calculated all of our endpoints for our right and left point already, we actually don't have to calculate any more points. The midpoint approximation will already use these points that we've calculated. But I do like to just usually write them down as well. So m of n. So we do actually need all the points from x of 0 to x of 6. So we already know that x of 0 is equal to 2. X of 1 we knew is equal to 7 over 3. X of 2 is equal to 8 over 3. X of 3 is equal to 3. X of 4 is equal to 10 over 3. X of 5 is equal to 11 over 3. And x of 6 is equal to 4. Now, you don't have to do this method that I used. Technically, you could, once again, just plug everything back into this equation. And you could technically try calculating it once again. But if you do like using this formula, I would only recommend it for right and left end. For midpoint, I would always recommend doing what I'm doing because it's so much simpler and you're less likely to make mistakes if you do it this way. So this is where things start getting interesting. We first write down our midpoint approximation formula. So we know that our delta x is 1 over 3, and our summation we know goes to 5 and starts at 0 of 1 over x of j. But for midpoint, remember, this x of j is actually very different. This x of j actually turns into x of j plus 1 over 2. So this actually turns into 1 over 3 summation of 5 of 1 over x of j plus x of j plus 1 over 2. A beautiful equation to look at. So once we just write all of this down, we end up with our very first term, 1 of x of 0 plus x of 1. X of 0 is 2, x of 0 is 8 over, x of 1 is 8 over 3. Sorry, 7 over 3. As you can see, it's also very easy to make mistakes here. Next, 1 over x of 1 plus x of 2. So 7 over 3 plus 8 over 3. Next, 1 over x of 2 plus x of 3 divided by 2. So 8 over 3 plus, we'll go 9 over 3 just to make this simpler for additions purposes. Next, 1 over, we have already done, remember, this is x of 0, x of 1, x of 2. So now it's x of 3. So 9 over 3 plus 10 over 3 divided by 2. Next, 1 over x of 4 plus x of 5. So you end up with 10 over 3 plus 11 over 3 over 2, all over 1. And then finally, our very last term is going to be 1 over x of 5, so 11 over 3, plus x of 6, which is just 12 over 3, all over 2. Now, this beautifully terrifying equation is what we have to simplify. And while it does look a little complicated, it is not actually that bad. And that is because this turns into 1 over 3. So I'm going to rewrite this 2 as 6 over 3, just to make it nice for operating on. So you end up with 13 over 3 over 2 plus 1 over 15 over 3 over 2 plus 1 over 17 over 3 over 2 plus 1 over 19 over 3 over 2 plus 1 over 21 over 3 over 2, finally plus 1 over 23 over 3 over 2. Now, this turns into 1 over 3 times. We're going to actually bring this, we're going to bring this up. So this turns into 13 over 6. So 1 over 13 over 6 plus 1 over 15 over 6 plus 1 over 17 over 6 plus 1 over 19 over 6 plus 1 over 21 over 6, finally plus 1 over 23 over 6. And then this once again gets simplified as 6 over 13 plus 6 over 15 plus 6 over 17 plus 6 over 19 plus 6 over 21, finally plus 6 over 23. And then once again, this is something I would recommend turning into using a calculator for. And then finally, your final answer should be approximately 0.692. Now, we have found all three approximations. Now, overall, it does seem a little complicated, but it is not anything crazy. Most of the time, you will get numbers nicer than this, but in the case that you don't, I would definitely recommend using a calculator. But overall, this is not a very complicated concept. It is something fundamental for anybody who is starting to get into calculus or integral calculus per se. And I do 100% recommend that you guys get familiar with fractions because you will be seeing a lot of them. All right, so that's pretty much it for the lesson. If you guys have any questions, feel free to leave them down below in the comments.